asking me to participate. This is really an exciting conference. And even when I was in high school, I rarely got invited to attend the coolest birthday party of the summer. So it's nice to be here. I don't know if this is a good title. It might be a bit misleading. What I mean is, the idea is to study combinatorial spaces, and to do that by borrowing ideas from from differential topology and differential geometry, but I'll mainly be talking about differential topology. And the goal is to then apply these new ways of studying combinatorial spaces back to other problems in mathematics. So there are two things I'd like to do in this talk. One is to really give an idea of the various applications. Some of these applications are real and some are complete fantasy. So I'll try to indicate which is which. And you can ask if it's not clear. And what I'd like to do is my theme, the sort of connecting theme for these various topics I'll present is the idea of a combinatorial dynamical system, which has words in common with words that showed up in some of the earlier lectures, but the ideas will be different. And I like to start with a fantasy application. So what I say in the next few minutes shouldn't be taken too seriously. But it will serve, I hope, to motivate the initial definitions. I want to start with, so our inability to prove that P does not equal NP shows that we don't really understand the structure of a computer program. And there's a growing community that believes that maybe topology can be useful in giving sort of computer science a little more of a rigorous foundation. And I'd like to start by showing one potential way of injecting some topology into some discussions in computer science. So here is a computer. Okay, so what a computer does, it has a list of initial configurations. I'm using the word configuration a little loosely. What I mean by configuration is all the information the computer needs to do what it does forever. The state of all the memories, whatever's on the input tape, the position of the tape reader, everything. And then there are also some final configurations. And in some of them, the computer, if it reaches that point, the computer will print out the word yes. And in the others, if the computer reaches that point, the computer will print out the word no. So there are four things that can happen. A computer program is a rule that tells you if you're at some configuration, which configuration do you go to next. And there are four things that can happen. One is if you start from some configuration, you can end up in a configuration where the computer prints out the word yes. Another is, say, the computer can print out the word no eventually. You can enter into a loop and never reach the bottom because you just keep going around and around. And the fourth possibility is you never reach the bottom because you just head off to infinity in some sense. Okay. So a typical problem is I tell you a subset of the initial configurations, and your goal is to write a computer program where for precisely that subset, you reach the bottom and the computer prints the word yes. And for everything not in that subset, the computer reaches the bottom and prints the word no. That's not possible for every subset of the initial configurations. If you can do that for the subset is called recursive. There are a growing number of known sort of subsets where you can write a computer program where in your subset you reach the bottom and it prints the word yes. But in the remainder, some of them reach the bottom and others loop around or do other things. That's called recursively enumerable. And there's a growing list of examples which are known to be recursively enumerable but not recursive, in the sense that any time you write a computer program that causes everything in your subset to come down and print the word yes, there have to be some closed orbits or things going off to infinity in the remainder. And the best known example of that is the halting problem, where the initial configurations represent computers and inputs and initial configurations, and you want the computer to print the word yes if, with that computer and that initial configuration, it reaches the bottom. That's recursively enumerable. You can have the computer in a trivial way print the word yes every time it reaches the bottom, but there will be lots and lots of orbits, closed orbits. And that's, in fact, what I'd like to understand is, for the halting problem in particular, the standard proofs are always there must exist at least one closed orbit somewhere. And in fact, if you think about it a moment, you can obviously see there have to be infinitely many. But what I'd like what I believe is there have to be lots and lots of closed orbits. Not just infinitely many, but in a sense, everything has to be. This is not right. But loosely speaking, if you make a halting problem that says yes whenever your computer halts, everything else has to loop. Well, that's not right, but morally speaking, that should be true. Okay. So that's one thing. We'd like to understand some sort of qualitative way or quantitative way of counting the closed orbits and saying the halting problem has to have lots of closed orbits. Well, so far I haven't told you how we might do that. When you write a computer program, you can't just draw these arrows arbitrarily. What makes a computer special is that it's a finite machine. And it can only look at a finite amount of information at a time. So just to be sort of precise here, suppose this initial configuration is labeled 21 and this is labeled 31, and we have a simple computer that can only read a single digit at a time. And suppose that it's in the initial configuration it reads the ones digit. Okay. Now whether the initial configuration is 21 or 31, the computer just sees the 1, and as far as it knows it's in the same state, and so it has to do the same thing. So for example, the instruction might be change the 1 to a 0. Or the instruction might be move over and reads the tens digit, or something like that. So the point is that it has to do the same thing, whether it's here or here. So one way of thinking about that is, in these two states, the computer has to move in a parallel direction. So to code that up, let's fill in this picture a little bit with a 2-cell, indicating that the computer is moving in a parallel direction, and put a little arrow there from the top edge into the 2-cell. Okay. So you can continue doing this, and there are various ways to do it. And then at some point they may no longer be parallel, and then we end up with an edge that doesn't know where to go, because the bottom vertices go off in opposite directions. So this is our approach to the problem. Starting with a computer program, there's a lot more structure that you have here that I'm not going to go into. This is enough to get us started. Starting with a computer program, we end up with a cell complex with arrows drawn on it. And what we'd like to do is understand the relationship between the topology of the cell complex we just built, the closed orbits, and these cells that don't know where to go. Okay. So that's the goal. So let's get started. We're going to start with a finite regular CW complex. So there are a number of reasons why what I'm telling you won't apply directly to the problem of computers. And one of them is the word finite. We're going to miss all the orbits that go out to infinity. And that's actually a more serious issue than the closed loop. So this is a serious restriction if your goal is to understand computer programs. And then a discrete vector field on this complex is going to be a collection of arrows, the way I've drawn them there. This is an example. So one way of saying that is a collection of disjoint pairs of pairs. I mean, just pairwise disjoint pairs. A cell and something in the boundary that's codimension 1. So here's a picture of a discrete vector field. I should mention that...
Pairwise disjoint pairs, that's sort of complicated.
So it's a collection of pairs so that none of the pairs have any cells in common. Is that... So if alpha and beta are a pair, I draw an arrow with the tail on alpha and the head on beta. And the fact that the pairs are pairwise disjoint, that means that every cell is either the head of a single arrow or the tail of a single arrow or neither. But it can't be the head of an arrow and the tail of an arrow or the tail of two arrows or anything like that. There's three possibilities. It's the head of a single arrow, it's the tail of a single arrow, or it's neither. None. Okay. So here's an example of a discrete vector field. I want to stop and emphasize 2 points. One is the things I'm saying will apply to very general cell complexes. They don't have to be manifolds or have any other well-defined structure. And the other is there are various approaches to studying the differential topology of combinatorial spaces. You might want to look at piecewise linear vector fields or something like that. So I use the word discrete to emphasize we're really just operating and we're not looking at any subset of the continuous objects. Okay. So one important class of objects are the zeros of this vector field. Say a cell is a 0 if it's neither the head nor the tail of an arrow. So the only 0 here is this 2-cell. And so the first kind of trivial observation that maybe indicates we're maybe on the right track is we can observe there's a Quackery Hop Theorem. This says the Euler characteristics of the complex is just the alternating sum of the of the zeros of the vector field. All right, and the reason is because the cells which are not zeros are paired up, and their dimensions are off by 1, so they have different parities, so in the alternating sum for the Euler characteristic they cancel out. Okay, so that's rather simple, but like I said, maybe we're on the right track. So, but we also want to understand the idea of a closed path or closed orbit. So here is a little bit sort of the dynamics. If V, perhaps I should have done, I always sort of give the kind of formal definition and then later comes the picture. Maybe I should have done this in the other order. But the picture is all that really matters. If you have a vector field V, a V path, oh, let me skip this and just go right to the picture. A V path is a sequence of cells where you start at the tail of an arrow, then you go to the head of an arrow, and then you go to another codimension 1 face. So you're allowed to go from the tail of the arrow to the head of the arrow to this edge, which is another codimension 1 face. That's a tail, so you can continue to a head, then another guy, then that's a tail, then you keep going.
Is an arrow always going from a codimension 1 phase to a phase?
Yes. Yeah. 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 So the arrow always goes from a codimension 1 face into the bigger guy. Okay, and a closed path is a sequence of guys like this is a closed path if the guy you end up with is the same as the one you start. And if it's made out of 1 cells and 2 cells, we'll say it has index 1. It's kind of the dimension of the width of the strip you made, and the length is the number of pairs you have to go through. So this is what a closed orbit is, or a closed path of our combinatorial vector field. And the main idea of the first sort of ideal...
That was a path.
It's not. It's closed if the last guy in line happens to be the same. So it's non-trivial closed path if alpha r equals alpha 0.
I mean, the previous picture you had arrows going...
Here? Okay, so what are some V paths? First of all, if you start at a vertex, which is the tail of an arrow, and you go to the head, which is an edge, you only have one choice for where to go next, because you have to go to another codimension 1 face. So you're forced to go here. That's the tail of an arrow, so you have to go here. And so this is a closed orbit here. If you start at this edge, then you go to the head of the arrow, then you can go either to this edge or this edge. But in both cases, you can't continue. You can only continue onward if it's the tail of an arrow. And in here, it's neither one of these is the tail of an arrow. So if you start here, after one step, you have to stop. Not all paths continue forever. Okay, so the main idea is that the topology of the complex is carried by the closed orbits and the zeros. So let's make this precise. We'll define the chain recurrent set. A cell is in the chain recurrent set if it's either a zero or it's in a closed path. Already here, if you know the sort of smooth theory, you'll notice a difference. That in the smooth theory of smooth dynamical systems, the chain recurrent set includes points which almost close up in some sense. And so here we see a major simplification, that we only need to worry about points that actually closed up. It's because when we look at things like this, we really kind of blurred our vision in this direction. And we're following kind of sets as they go along. So if it almost closed up, and kind of a smooth thing, after we blur it and just keep track of cells, it will actually close up. So we only need to keep track of actual closed orbits. Okay, and the chain recurrent set can be decomposed into basic sets where two guys are in the same basic set if they're contained in some closed orbit. So that's the general definition. Here's the example that we've been looking at. The chain recurrent set is made up of two basic sets, the one that consists of this single closed orbit and one that consists of this zero, the single zero of the vector field. Okay. So from here we can see basic sets come in two types. There's a basic set that consists just of a single zero of the vector field, and a basic set that's a union of closed paths of index p. And now we can, in a slide or two, become relevant to calculate the homology of a basic set modulo its boundary. And we notice that if the basic set is just a zero, then it's a cell, and the homology of a cell relative to its boundary is just one-dimensional, and it's in the degree equal to its dimension, zero otherwise. And if you have one of these more complicated things, the union of closed orbits, the homology only contributes in certain dimensions, but it's a little harder to say what it does contribute. So here's the first result. Remember, our goal was to find some sort of relationship between the topology, the zeros, and the closed orbits. So here's the first such result, that if we define Morse numbers, m sub I is you sum over all the basic sets, the dimension of the ith homology. Then you can also look at the Betti numbers of your complex, that you have the Morse inequalities. Essentially all of the homology of the complex has to be represented in this homology, either of the zeros or the closed orbits. Okay. So here are the strong Morse inequalities, and the weak Morse inequalities is somewhat simpler to look at, that this mi is always bigger than or equal to bi. So this is along the lines of what we were aiming for. We wanted to prove that this computer program had lots of closed loops. So if the complex you build has a lot of homology, then the computer program has to have a lot of closed loops combined with edges that don't know where to go, right? Combined with cells that don't know where to go. So, but what I've written here is not quite strong enough to actually study computer programs for a variety of reasons. So let me indicate how you would prove such a thing. The proof is rather simple as well. Define a Lyapunov function to be a function that if you move along any v path, the function is strictly non-increasing, and it's decreasing except along the chain recurrence set. That if these guys are in the same basic set, then the Lyapunov function will stay constant, otherwise it decreases. And the simple theorem is that every vector field has a Lyapunov function. Okay. So let me write down one to show you one for the example we've been looking at. Here's a Lyapunov function for this example. So this function is constant. It's constantly equal to 0 along the closed orbit, and along any other v path it's strictly decreasing. So for example, we talked about this edge going to this 2-cell going to this edge, so the function goes 6, 5, 3. Or we can go from this edge to this 2-cell to this edge, and it's 6, 5, 1. And the existence of a Lyapunov function is enough to prove the theorem. Namely, the Lyapunov function gives us a coherent way of building the complex one step at a time by adding the cells in the order prescribed by the function. So define the level subcomplex. If C is a real number, the level subcomplex is you just add all the cells whose value is less than or equal to C, and then add in all their faces to get a subcomplex. So let's do that for this example. So that's the Lyapunov function I wrote down. And here is the construction of the complex one step at a time, adding the cells in the order prescribed by the Lyapunov function. So when C is 0, we have to add the entire closed loop. When you move up to 1, you throw in this edge, but you also have to throw in this boundary vertex to make it a subcomplex. So you keep going until you get the entire complex. And we can see now why only the basic sets contribute to the topology. So for example, this 1 was not part of a basic set, so why did the topology not change, up to homotopy anyway, when I added this edge? Well, the 1 was not part of the basic set. That indicates that the v path that comes from this vertex to this edge to this vertex is not a closed path, so the function has to strictly decrease when you go from here to here to here. In particular, the tail of the arrow, this 1 is the head of the arrow, the tail of the arrow has a bigger number. It's a simple observation. When we added the 1, it's not in the basic set, and that means its tail has a bigger number. And that means when we add the edge, we also have to add the vertex to make it a subcomplex. So that's generally what happens. If you add something not in the basic set, you have to also add the tail of the arrow. And so when you're done, you have what's called a simplex, or a cell with a free face. It's a codimension 1 face, which is not the face of any other simplex. And so what's left, what's simplicity collapses in the case of onto what came before. You can push in this cell along the free face. It's a special type of deformation retract. And so up to homotopy, nothing changes. On the other hand, if you look at this 0, this 2-cell, everything in its boundary has a lower number. Okay? So when you add in this 0, or any basic set, you glue it in along its boundary to what you had before. And then there's a standard step in Morse theory that if you glue in something along some set, the most the homology can change is the relative homology of what you're gluing relative to the gluing set, right? Basic fact. So, and that's the Morse inequalities. Okay. I just want to emphasize that between basic sets in Morse theory, for example, things change by a smooth deformation retract. In this theory, between basic sets, things change by simplicial collapse. The bigger things simplicial collapse onto smaller things. The equivalence relation generated by simplicial collapse was defined by J.H.C. Whitehead, whose name will show up a couple times, and he studied some implications of this idea. The equivalence relation generated by simplicial collapse is called simple homotopy theory, and so these techniques seem to be particularly useful for questions in simple homotopy theory. Okay. Okay, let me mention some extensions. So that just told us a little bit something about how many, in a sense, how many closed paths there are. You can work a little more precisely. You can get information about how many closed paths there are in each free homotopy class by choosing a representation of the fundamental group. And then there are other zeta functions you can write down, but this is sort of a natural one. It's sort of the standard form of a zeta function, sum over k, z to the k over k, and then you sum over closed paths of length k and index p. But instead of summing just a 1 for each path, you put the trace of a holonomy around the path, and you throw that into the zeta function. This plus or minus 1 is just a question of orientation. Remember, closed loop is a path, and there's a question of whether when you go around, I mean a strip, I should say. There's a question when you go around the strip, does the orientation agree with what you started with or not? And that's the plus or minus 1. So you can write down this zeta function. And here's the theorem that the zeta function has a positive radius of convergence and can be analytically continued to a meromorphic... oh, sorry. Thanks. This zeta function can be analytically continued to a meromorphic function on the entire complex plane. And if each of the basic sets is acyclic, has no homology with respect to these twisted coefficients, twisted by the representation, if each basic set is acyclic, then you can express the Reitemiser torsion. Then the value, then the zeta function is regular, it's z equals 1, and its value at 1 is related to the Reitemiser torsion of the complex. There's another factor having to do with this. I haven't defined what this is. We'll get to it later. This is the Morse complex, which only depends on the zeros. So what we've done is you've written the Reitemiser torsion of the complex as a product of things, one coming from just the zeros of the vector field and one coming from the closed orbits. So one way of proving this is to study the asymptotics, deform the standard chain differential by the Lyapunov function and study what's happening to sort of each of the terms in the sequence. This is kind of a standard method of proof in this sort of thing these days. And one interesting comment is that this theorem is very closely related to a number of results for smooth or continuous dynamical systems by David Fried, and more recently by Hutchings and Lee and Hutchings. And Hutchings and Lee were interested in the fact that this formula is conjecturally related to Seiberg-Witten theory. And the relationship is, so Taubes has shown with some very beautiful mathematics that the Seiberg-Witten invariant of a symplectic four-manifold counts pseudo-holomorphic curves in the four-manifold. And if your four-manifold is a three-manifold cross a circle, then it's also known that the Seiberg-Witten invariant of the four-manifold is the same as the Reitemiser torsion of the three-manifold. And so the conjectural part is that Taubes work, if you want to work directly on the three-manifold, the symplectic form restricts to a closed one form, and the pseudo-holomorphic curves restrict to give closed orbits of the vector field dual to the closed one form. So that this formula, in the case of a vector field dual to a closed one form, is in some sense a formula for the Seiberg-Witten invariance of the four-manifold. So I think this is kind of interesting in the sense we started trying to prove P equals NP, and somehow we ended up at the Seiberg-Witten theory. That's kind of a... Okay. So just a comment. I'm not going to say anything more about it, but in this theory I've found sort of an appropriate notion of a closed one form. In fact, a combinatorial differential form that seems appropriate for this theory, and in particular combinatorial differential one form that's dual to this notion of a vector field. And so you can develop a Novikov Morse theory, or what's called multi-valued Morse theory, which I won't mention anything more about. Here are some fantasies. One is, they're not just me, there are a lot of people who would love to find a combinatorial formula for the Seiberg-Witten invariance. So maybe the formula I wrote down is some sort of clue, because we know more or less how to approach it for a three-manifold across a circle. Maybe it's a clue. Another is to develop a combinatorial symplectic theory. There's also a growing number of people trying to find such thing. Again, since we have a notion of, I know what a combinatorial closed two-form should be, at least to be compatible with the things I've told you. So sometimes I think maybe I'm close to such a thing, but there are real subtleties here. One goal is not just to make symplectic theory combinatorial, but there's, of course, in quantum theory, where you have to do ill-defined integrals over infinite dimensional spaces, one sort of prescription for this, to make this sort of thing well-defined, is to make everything combinatorial, and then the infinite dimensional integrals hopefully will become discrete sums over things that are well-defined. And so that's another motivation for doing this, and it's not just a crazy idea. I've been able to do that, well, wherever the slide just went. I've been able to do that for the case of Morse theory, where Witten gave a proof of Morse theory, where in the middle there are some ill-defined path integrals. But if you follow just exactly what I've written here and go through Witten's proof of Morse theory using the deformation of the differential that I wrote down, where Witten comes across an infinite dimensional path integral that's not well defined, here we do get a discrete sum over paths of the sort that I wrote down, and everything is perfectly well defined. So I'd like to, of course, see other cases where maybe that sort of thing would work. And here's a question: which smooth vector fields can be triangulated? And what I mean by that is, if I give you a smooth manifold and a smooth vector field, when can I triangulate the manifold and come up with a combinatorial vector field which in some sense captures the dynamics? This is very closely related to the approach to a smooth vector field using Markov partitions, but it's slightly different. So there are classes of vector fields that I know how to triangulate, including gradient vector fields. And in fact, Dennis suggested last time I talked to him that it seemed to be closely related to the idea of the stability of a vector field. Meaning if it changes the vector field a little, the dynamics don't change, which seems relevant because we're blurring our vision a little and hoping to understand it that way. So they may be more or less equivalent notions, but I'm not sure about that. Okay, so what I'd like to do now is specialize to the case of Morse theory, from general vector fields to gradient vector fields. So say a vector field is a gradient vector field if there are no closed paths. Okay? In this case, the chain recurrence set are just the zeros, and the Morse numbers are just the number of critical points. Right? There's none of the other complications. You know, if you're more comfortable with Morse theory being presented from the point of view of the function and not the vector field, you can certainly do that in this case as well. It's sort of simpler to present it in terms of the gradient vector field. So here are some things that we can just deduce from our proof of the Morse inequalities earlier. We noticed that whenever we added a critical cell, we just glued it onto its boundary, glued its boundary onto what we had before. So just looking at the proof, you can make the statement that if K is a complex and V is a gradient vector field, then this complex is homotopy equivalent to a CW complex with exactly one cell of dimension P for each zero of the vector field of dimension P. That was followed exactly from our proof. We just glued things onto their boundary. And of course, you can refine this to make it a statement about collapsing. And here's just a special case of what you can say, that the complex collapses to a point. You can get all the way from your complex down to a vertex, collapsing all the way if and only if there's a gradient vector field with exactly one zero. That zero has to occur at a vertex. The rules imply the zero occurs at the vertex, and everything then collapses to that vertex. Well, Whitehead, in his investigation of collapsing, proved that a combinatorial manifold with boundary which collapses to a point must be a combinatorial ball. This is a really great theorem. It's one of my favorite theorems. So this is an example of, although I've been working with general cell complexes, if you happen to start with a combinatorial manifold, you get stronger conclusions. So here's a corollary. If K is a combinatorial manifold with a gradient vector field with exactly two zeros, then K is a combinatorial sphere. And the proof is, if the vector field has two zeros, take out one of them. What's left only has one zero, so collapses, and therefore must be a ball. And then what you had is a ball with just a cell glued in, so it had to be a combinatorial sphere. Well, at this point, you think, well, maybe we can prove the Poincare conjecture by just going a little further. And you can, but in the same dimensions that it's already known. So let me give you one. But in some ways it's simpler. So here's one step in the proof, not the hardest step by any means, but here's a step in the proof of the higher dimensional Poincare conjecture with H cobordism theorem or S cobordism theorem, the fundamental cancellation theorem. So here's how you prove the Poincare conjecture in higher dimensions, loosely speaking. You put any old Morse function on your homotopy sphere, and then you cancel out the critical points in pairs. You show you can do that until you get down to a Morse function with just two critical points, and then it must be a sphere. Okay. And here's the key step that tells you how to cancel out critical points in a really good situation. That if you have a gradient vector, suppose you have a gradient vector field, and you have two critical points which are off by one dimension, and there's exactly one path from the big guy to the small guy. Then you can cancel them out in the sense there's a gradient vector field with the same zeros except those two are no longer critical. Okay. So the proof in Milner's original paper is of this, Morse's paper is 27 pages or so. And in John Milner's book Lectures on H cobordism, he has a proof that's roughly 9 or 10 pages. And here's the proof in the combinatorial setting. This is the complete proof. Right? Here's beta, and here's alpha, and they're both zeros. They're neither heads nor tails of arrow. And here's the unique gradient path from beta to alpha. What you do is just change the vector field to this. And you're done. Alpha is no longer critical because it's the tail of an arrow. Beta is no longer critical because it's the head of an arrow. And what we just need to check is that this is a gradient vector field, that there are no closed orbits. But if by doing this we had created a closed orbit, that would mean there have had to have been another gradient path from beta to alpha to begin with. Right? QED. Okay. So here you can see why the combinatorial theory is in some ways simpler than the smooth theory. Namely, this is the proof in the smooth theory. You start with the unique gradient path, and then you turn all the arrows around. But of course, then you have to turn all the nearby arrows around too. You have to interpolate between the vector field as it is outside some neighborhood and the vector field along the gradient path where you've turned all the arrows around. So you have to turn all the nearby arrows a little bit and making sure you don't create any closed paths or anything like that. So it's not that the proof is hard in any conceptual way, but keeping track of the details is a little tricky, and you just don't have to do that in the combinatorial world. Okay. Here's one one application of this. For example, suppose K is a connected triangulated 3-manifold with boundary, then K collapses if and only if there's a gradient vector field with no critical 1 simplices. This is all you need to check. Because if you have a gradient vector field with no critical 1 simplices, this cancellation theorem tells you can automatically cancel out the critical 2 and 3 simplices and get down to one with no critical cells, and so it collapses. And this is kind of a simple observation, but there are a number of papers I found where three complexes were shown to collapse. And this observation can be used to greatly simplify some of the proofs. Okay. So now let me describe some applications of this. So these are applications to combinatorics. In the last couple of years, a growing number of combinatorialists have been using these ideas to actually study the homotopy type of simplicial complexes arising in combinatorics. Here's one class that I just mentioned, that in Vasiliev's work on knot invariance, he looks at the space of singular knots and then constructs a simplicial resolution. That space is highly singular. Constructs a simplicial resolution, and which is rather complicated, and a simplicial complex that shows up as the link of a vertex in this is the complex of not 2 connected graphs and also the complex of not 3 connected graphs. And the homotopy type of those simplicial complexes was determined by using this discrete Morse theory. This work, by the way, by these people is really amazing. I mean, they start with a very complicated simplicial complex, and then by hand they construct a gradient vector field, a pairing of the simplices, and then check that there are no closed orbits. and then use the Morse theorem to deduce what the homotopy type is. And I also like this paper by Eric Babson and Patricia Hirsch, where they're studying partitions of an integer, a simplicial complex resulting from studying partitions of an integer, and they use this cancellation theorem quite heavily. And I like the idea that sort of a technique that arose in the proof of the Poincare conjecture is now being used to study set of partitions of an integer. I think that's kind of a surprising sort of development. So the next application I would like to go into a little detail about is an application to computer science. So it's what made me start thinking about sort of the introductory example a bit. So here's a problem from computer science, the problem of evasiveness. And I'm going to present a very topological version of the problem. So if you see evasiveness in the computer science literature, it may not look like this, but this sort of is a general question. So suppose you start with a simplex of dimension n with n plus 1 vertices, and K is a subcomplex. And both the simplex and the subcomplex are known to you. And then there's a face of this simplex which you don't know. And your job is not, it's a search problem. Your job is not necessarily to figure out what that face is, but your job is to just figure out, is that face in the subcomplex? So it's a yes or no question. Right? Is it a face of the subcomplex? And you're allowed to ask questions, is vertex I in my face? Right? And then you get yes or no answers, and you continue to ask questions, and you're allowed to stop asking as soon as you know whether it's in the subcomplex or not. Okay. And say the subcomplex is evasive, this is where the word comes from, if no matter, obviously after asking n plus 1 questions, you can do it. Because you just ask about each vertex, and you know exactly what sigma is. So you certainly know whether it's in K or not. The question is, can you do any better? Right? And say the complex is evasive if you cannot do any better. That is, no matter what strategy you choose, there's always some face that makes you ask all n plus 1 questions before you can tell whether it's in K or not. Okay, and here's the Kahn, Sachs, and Sturtevant proved an interesting relationship between the topology of K and its evasiveness. If the homology of K is not 0, this tilde means reduced homology. So if the reduced homology of K is not 0, then K is evasive. In fact, they proved something slightly stronger having to do with collapsing, but I'll get to that later. So here's an example of their theorem. Here's a 2 simplex, and I've indicated K. K is the union of an interval, this 1 simplex and this vertex, so it does have some reduced homology. And here is a guessing algorithm. So what I mean by this is you ask, is V2 in your face, in the face sigma? And if you get the answer no, then ask, is V0 in sigma? If you get the answer yes, then ask, is V1? So this is an algorithm for determining which question to ask about. And actually, you don't have to ask about, you don't have to go all the way down the chain. Suppose you ask, is V2 in sigma? And you get the answer no, V2 is not in sigma. Well, then you can stop. Because every face of this 2 simplex, which does not contain V2, is in K. Right? So you're done. Well, you say, well, then I know that sigma is in K. Right? But if you get the answer that V2 is in the face sigma, then you have to ask further questions. And now let's check for when do we have to ask the final question. Notice that we don't, if we say V2 is in the complex, and then V1 is also in the complex, I ask about V1 and I get the answer yes. If V2 and V1 are both in the face sigma, then I know it can't be contained in K. So I can stop. The only time I have to ask the final question is if I get the answer yes when asking about V2, no when asking about V1. Then I have to ask about V0. Okay? And so I have to distinguish between the cases that it's just the vertex V2 or that it's the edge V0 and V2. So say that the evaders of this guessing algorithm are these 2 faces. If sigma is either one of them, you have to ask all the questions. Otherwise, you can stop before getting to the end. Okay. But, so here's, this is a good example because it shows how discrete vector fields show up sort of in nature. This guessing algorithm automatically gives you a discrete vector field. A discrete vector field is a collection of pairs. Well, this guessing algorithm gives you a collection of pairs, right? Namely, pair up the simplices that you don't distinguish between until you ask the last question, right? So pair up this vertex V0 with the edge V0, V1. Pair up the vertex V2 with the edge V0, V2. Pair up the edge V1, V2 with the 2 simplex. Right? And that gives you a collection of pairs. So there's one minor technicality, that it pairs up something with the empty set, and I haven't been allowing pairing with the empty set. So this, I'm going to fudge things. So everything is that's why what shows up in the theorem is reduced homology and not homology, because the empty set shows up here and didn't show up in the original case. Okay. So here I've drawn the vector field that you get, the vector field consisting of those three pairs. Okay, here's the theorem. The vector field you get from a guessing algorithm is always a gradient vector field. Right? It's always a gradient vector field. Okay, so now, remember K was just this edge and this vertex. We can restrict this vector field to K by just, instead of putting up the next slide, we can restrict the vector field to K, which means just take the arrows where both the tail and the head are in K. Right? So we're not allowed to do that arrow because it involves cells not in K. And we're also not allowed to do that arrow because the tail's in K but the head's not in K. So when we're done, we have just this arrow. So this is a vector field on K. When you restrict a gradient vector field, you always get a gradient vector field, because if there are no closed orbits to begin with, if you rule out some arrows, you have fewer paths than you had before, so you can't suddenly have some closed orbits. So when you restrict to K, you have a gradient vector field. But it has some zeros. Right? Initially, the vector field had no zeros. Everything was paired up. But now we have some zeros. But what are the zeros of the vector field now? The zeros of the vector field, like this vertex is going to be a 0 because we have to get rid of that arrow. The zeros are precisely the ones where we had to throw out the arrow because they were the tail of the arrow, but the head of the arrow was not in K. That's why we had to throw out the arrow. So they're precisely the cells in K where we can't distinguish them from some cell not in K until the last question. Okay? So those are precisely the evaders of the guessing algorithm. So the critical points of this Morse function are precisely the evaders of the guessing algorithm. Right? So that's what this slide says. You restrict to K, you get a gradient vector field, and the evaders of the guessing algorithm are precisely the critical points. And so then you can apply the Morse inequalities, and you get a quantitative version of the original theorem, that there have to be at least as many evaders to account for the homology of K. And there's actually a 2 here because the evaders come in pairs, something in K and something not in K. Right? So the number of evaders in K is just bigger than or equal to the dimension of homology. So this is an example where sort of this idea of imposing some topology on a search algorithm gives you a quantitative refinement of sort of a yes or no answer that computer scientists came up with. So this is hopefully, or I think maybe this can be done for other sorts of problems. And you can also get a number of refinements of this, but here's one refinement that they did prove, that suppose K is not evasive. If K is not evasive, then there's a guessing algorithm which results in a gradient vector field with no zeros. Right? Well, we know that if it has a gradient vector with no zeros, it collapses. So if it's not evasive, then it collapses. And the guessing algorithm, they had a different proof, but our proof is if it's not evasive, it has a good guessing algorithm. Almost by definition, a good guessing algorithm tells you how to collapse. It gives you a vector field with no zeros.
Did you restrict your questions to me only asking if the vertex is in K or not?
If the vertex is in sigma or not. Yeah. Right. So in this case, there are other problems where you'd like to ask other types of questions, and this will not apply in a direct way. Okay. So this is an interesting application, I think, to computer science, and I think maybe there's some potential to make quantitative other sorts of results, but I don't know how to do that quite yet. Okay, so now let's look at some applications to more topological issues. We saw that with the fundamental cancellation theorem, that you know that if there's exactly one gradient path between critical points, then you can cancel them out. And this indicates that if you, instead of just know something about the zeros, if you know more precisely how many gradient paths there are from one critical cell to another, you can probably make more precise statements. And so the next few applications are all along these lines. So here's the first one. Here's a way of turning the Morse inequalities into the Morse equalities. That if you have a gradient vector field, define a complex inside the standard cochain complex, where only look at the cochains which are supported on the critical cells, right? So the critical cocells. And we can define a differential. This is, again, it's hard to see what this means by just looking at it. But the differential of a p cell is you sum over the coefficient of a critical p plus 1 cell is you just count gradient paths from the boundary of the big guy to the small guy. It's exactly the sort of gradient path that showed up in the cancellation limit. So here's an example of the sort of thing you count. These guys are oriented cells, so you count them with plus or minus depending on whether the orientations agree or not. And the theorem is that the square of this differential is 0, and this complex calculates the homology of the underlying complex. So this complex goes under lots of names. It's been the Morse, Smale, Witten, Thom, Floor complex. Another point I want to make that kind of shows the simplification going from the smooth theory to the combinatorial theory is in the smooth theory you generally have to restrict from a Morse function what's called a Morse-Smale function, where all the stable and unstable cells intersect transversely. There is no such condition here. This theorem was for a general cell complex and a general gradient vector field. The point is that these vector fields already have themselves layered off into the appropriate dimensional cells, and so they only intersect when they're supposed to. Right? There's no spurious intersections, and so you don't have to. There are just no issues of transversality. I shouldn't say that, no issues. So we'll see some, but in this setting there are no issues of transversality.
So it doesn't have to be a manifold, right?
No, here there's still just a general cell complex.
Quackery Hop Theorem, you have a manifold F goes to minus F fails here.
That's right.
It's not a
And right, we shouldn't expect Quackery to. I mean, we're just worried. But an important point that will show up in a few slides is that if you have a combinatorial manifold, and you look at its dual cell complex, then if f is a Morse function on the first guy, then minus f is a Morse function on the other guy. Or said an equivalent way, if you have a gradient vector field on a combinatorial manifold, and you look at the dual cell complex, then you reverse the arrows, switch the role of heads and tails, then that will be a gradient vector field on the dual cell complex. Okay. I was holding a slide. Here it is. Nope. Here it is. Okay, so that was sort of how to construct the cohomology exactly. Also, any operation on cohomology, I meant to change that word because I didn't like it. Any operation on cohomology which can be defined on the level of cochains automatically can be represented in this theory for general cell complexes by counting gradient paths. And this is, Betts and Cohen and Fukaya independently did this in the smooth case, showed how to see cohomology operations in smooth Morse theory by counting gradient paths. And so I'm just going to give an example of the cup product. And so I want to map, so given two cohomology classes, I want to know what their cup product is. The interesting thing is you can express the first cohomology class in terms of one Morse function, or one gradient vector field, the second cohomology class in terms of a second Morse function, and then define the cup product in terms of a third Morse function. And again, there's no genericity assumption, no transversality assumptions between these three Morse functions. So if you give me two critical cocells, I want to define a map that gives me a sum over the cocells of the critical cocells of the third guy, and it's a sum over triples of gradient paths. Let me just show you a picture. Here's a picture of the kind of triple we're counting. We're taking the cup product of alpha 1 and alpha 2. They're the duals of these critical cells. And alpha 3 is critical for the third guy. And you count schematically Morse embeddings of this Y shape. Right? Exactly as in the smooth theory. You start from the critical guy and you look at gradient paths, and you have to get to a triple where I have here cells A1, A2, A3, where A1 cup A2 is A3, plus or minus A3. And then you split off, and out from A1 goes to one guy and A2 goes to the other guy. And by counting these sort of discrete objects, you get a map. Well, the theorem is that this map induces the cup product on cohomology. Okay. And like I said, any map on cohomology which can be represented on the cochain level, has any cochain that is induced by cochain map, automatically can be represented by counting critical guys and gradient paths between them. Okay. Now here's something that I don't quite know how to do, and I'll tell you what I can do, what I can't do. So this is something that's in progress. So Fukaya showed how to define a finite type invariant of a rational homology S3 by counting Morse embeddings of this shape. Right? So you have 3 generic Morse functions, and then you count them on a homology S3. You count things that look like this. And this is conjecturally maybe the same as the perturbative Chern-Simons invariant and Axelrod and Singer defined. So what I like to say here is that if you have a combinatorial manifold, then the same thing works. You can do this in combinatorial theory, namely picking 3 combinatorial Morse functions. You can define an invariant. Now here, it's interesting because we do need, so one question is, everything up till now worked for just a general cell complex. Why do we need combinatorial manifolds all of a sudden? And the reason is that although it looks like we have 3 Morse paths starting at one point, ending at another, a better way to think of this is a collection of loops, where you go up here and then go back, and then go up here and then go back. And in smooth Morse theory, it's no problem. I mean, flowing down F in this way is the same as flowing down minus F in that way. But in the combinatorial theory, if we're going to make sense out of this, we really need to be able to flow backwards and forwards along our gradient paths. And that's why we need to work on a combinatorial manifold where minus F is a Morse function. Okay.
Did you have to take it? The word embedding is used?
No. Not.
Kai was counting embedding, just let's talk about it.
It's actually, well, I shouldn't say embeddings. These paths are allowed to cross. I mean, generically they don't. But, so what I know is that this definitely works for combinatorial manifolds. But what I don't know how to do yet, which I really would like to do, is understand just sort of a way to count these things combinatorially. I mean, right now the intersection, I know that everything that Fukaya did just works. I mean, the Morse theory works to give, so the same proof works. In that sense, I know how to define the invariant by having things intersect sort of in the topological sense. But I don't know sort of precisely how to write down sort of a combinatorial form. Well, I think I know what the right counting is. It's much more subtle than the counting we were doing before. But I think I know the right formula for what we're counting. And then what I haven't been able to do yet is just sort of a direct proof that this combinatorial counting is an invariant under all choices. But the combinatorial counting I have in mind doesn't see, I mean, again, I'd like to see exactly as before that there's no transversality condition. Right? So what I'd like for the combinatorial theory to be able to do is, so Fukaya had trouble showing that this invariant was the same as what Axelrod and Singer did. In some sense, what they did is define the same invariant where all 3 Morse functions were all the trivial Morse function. I mean, that's and then you want to see some way of getting from sort of where all 3, which is completely, of course, non-transverse and non-generic, and to get from that triple to a generic triple. And he suggested maybe you can use that through the Witten deformation. But what I think, I was hoping to have it done by now, of course, but I don't. What I think should happen is that there should be one combinatorial formula, in this case, that works independent of transversality conditions. So you can see in one setting a combinatorial version of the Axelrod-Singer formula and a combinatorial formula version for the Fukaya form, and see directly that they're equal. So I should have mentioned earlier, for example, that in this case of the cup product, there really is no transversality condition or no genericity condition, so you could have taken for your gradient vector field the 0 gradient vector field. Right? No arrows, V1, V2, and V3 are all just 0. In that case, you're just recovering the standard cup product again. So you're not getting anything new, but it all fits together. There's no exception made for the kind of trivial case. Okay, so for sort of the last, let me just, I have a couple more applications I could have talked about. Instead, let me just tell you what one of the main ingredients is to the theory for almost all the applications. And that is, there's sort of 2 ways. If I give you a smooth vector field on a smooth manifold, there are 2 ways to study the dynamics. One is you start with a point and then see where it goes. Right? Look at the flow line through that point, and that's kind of the approach we've been taking. The other way to study a vector field on a smooth manifold is to say flow the entire manifold for time t. Right? Then you get a diffeomorphism from the manifold to itself that you can study. And I mean, obviously they're usually interchangeable, but they're slightly different philosophies. And we've been talking about following a point in some sense, but you can also you can also talk about the flow of a vector field, and this is a really important tool, so I'll just show you how it works. Given a vector field V, we can define a flow. It's a discrete time flow from p chains to p chains, oriented chains to oriented chains, and the first thing is we have to think of this map V, which was a collection of pairs. Think of it as mapping the tail to the head. So it's a degree 1 map on oriented cells. To make it, to have it map on oriented cells, you have to have the orientations match up correctly. So what this rule says, that if here's alpha and here's beta, you have the arrow like this, so that the boundary, so that in a sense the orientations don't agree. They're opposite. And that's the idea that this beta is a tangent vector leaving alpha. So this is the rule. You have it be a map on oriented cells like this, and then you define, this is a formula for a discrete time flow. 1 plus, first do the boundary, then do V. Remember, boundary is a degree -1 operator. V is a degree +1 operator, so this maps you from p chains to p chains. And for the last slide, let me give you an example. Here is, I should have drawn, here's a two-dimensional complex. I've drawn 3 arrows to indicate the vector field, and I want to know what this edge E flows to. So this is an oriented edge. So it flows to, the rule is, maybe I should put it down here, the rule is 1, the map is 1 plus boundary V plus V boundary. So it applied to the edge E, you get E, that's the 1. And then you apply V. V is this 2 cell, the head of the arrow oriented this way, and you take the boundary of that, you get this closed 1 chain. And then you take the boundary of E, which is a +1 here and a -1 here, and apply V to that. V of this vertex is this oriented edge, V of minus this vertex is this oriented edge. Then you add them up, and you get this 1 chain. So the flow operator takes this edge E, this oriented edge E, to this 1 chain. Okay? And they're coupled, so this is a couple of the theorems I wrote down follow immediately from understanding what happens. In particular, one thing you can see is that this flow operator, -1, is the boundary times something plus something times the boundary operator. So it automatically induces the identity map on homology. Right? And V is the algebraic homotopy operator. So, for example, this stuff about counting up gradient paths to see that you're inducing some map on homology really just is understanding this flow map and knowing that each time you apply it, you're not changing the homology at all. Okay. So I guess I'll stop there. Thank you very much.
Are there any questions? Do you have any thoughts on the loop space of a combinatorial vector?
Well, I have lots of thoughts on the loop space. Yeah. I don't understand the case of the loop space as well as I... So philosophically, what I think of is if you triangulate a manifold, that's like giving yourself a Riemannian metric. And so there are... And of course, if you look at the loop space of a Riemannian metric, there's a natural Morse function, the energy function. So there should be a natural gradient vector field on... There exist various combinatorial models for the loop space of a simplicial complex, due to Kahn and others. And yet I don't... There are some candidates... I don't know... this is one of the most frustrating points in the theory. I really was expecting to just see a natural gradient vector field on the combinatorial model for the loop space, and I don't yet. There are things that come close, and so you touched on one of my major disappointments in the theory. So yeah.
Do I understand it right that when you that this invariant that was suggested to you by Kaya, which counts those patterns is actually an invariant coming from an invariant of the combinatorial loop space, because you're sort of counting the situations when three loops come together in this closed I of pattern.
I don't know if I mean, so I would say it's an invariant of the combinatorial structure. I mean, you know, the underlying combinatorial structure of the smooth manifold. But I guess I don't. I mean, if you just gave me the loop space, I'm not sure if I would know how to count. I mean, because we're only counting particular loops.
Yeah, but those we follow.
Yes. Right. So it goes back to the first question. I mean, that's a good point. If I knew how to lift a Morse function to if I knew a good way of lifting a Morse function to a flow on the loop space, which I wish I did know, then I would. Yeah, then I would agree that you could then express things in terms of just some intersections in the loop space. But I don't know how to do that.
C on the last slide is chain homotopy. The ones that arise this way, do they have any special abstract property that you can characterize? Which chain homotopy?
That's a good question. I haven't even thought about it. I don't know. That's a good question.
Are there any further questions? Then I suggest we meet again maybe in 20 minutes, 20 hours. We're a little bit behind.